I'm very pleased to be here and to talk to you about this subject today. We're going to be hitting on the subjects of, it says distributed generation. The IEEE is really trying to get us to use the term distributed energy resources. The reason being that storage can be generation or load, so just calling it distributed generation might be confusing as to whether it includes storage. I'll still use the term DG, and hopefully we'll all understand what I mean. We're going to talk about some of the interconnection and integration issues that we're seeing. Most of what I'm going to talk about today is distribution centered. There will be a couple of transmission level topics, and a lot of the topics overlap, but my own experience is largely at like the 15 kV level and below. So that's most of what I'm going to talk about today. Just a brief word about the company that was mentioned here. Northern Plains Power Technologies is headquartered in Brookings, South Dakota. The company was officially founded in 2005, and we've been specializing in transient modeling of power systems. We do a lot of EMTP type modeling. So all the EMTP flavors, MATLAB Simulink, Digital Power System, Power Factory, that sort of thing. We work on distributed generation interconnections. We do a lot of work with what I have called here low inertia systems. You've all heard the term microgrids, and I actually try to avoid that term whenever possible, but we work on systems that are smaller systems that usually can connect to or disconnect from the mains, but they may also be standalone systems, islands, remote communities, that kind of thing. So the reason we use low inertia instead of microgrid is because there may not be a grid tie in some of these cases. So a lot of things that may have like a diesel backbone or something like that, and people want to start adding solar and storage, that's where we would get involved. And you can see some of the specific things that we've worked on there. I don't want to belabor that point. Yes, I do have an undergraduate degree in music. I effectively double majored in physics. So I had a lot of the material science and calc and all that kind of stuff. So it doesn't sound as weird as I said that backwards. It isn't quite as weird as it sounds. But anyway, to introduce the topic just a little bit, I wanted to hit on some of the drivers that have led the system to be where it is today. Why does the system look the way it does? There are actually three. Unfortunately, for some reason, I only listed two of them, but the main ones have been reliability, maximum reliability, minimum cost, and then the third one, of course, is maximum safety. That's the one that should be up there and isn't. We have, over the last, 120 some odd years, optimized the system pretty tightly for these three factors. And I would say, as a whole, the industry has done quite well in this regard. Reliability is typically over 4 nines in most places. Availability. The cost, electricity is, if you look at historical dollar values, electricity is quite a bargain. It's a pretty inexpensive energy carrier. Our safety is very good. Obviously, safety is always a concern. We've got kilovolts hanging in the air over people's heads, but generally speaking, things have worked pretty well. So the system is, I would argue, pretty well optimized according to those three parameters. So, unfortunately, things have started to change. And everybody knows that if I've got the system optimized with three variables, three factors, if I'm going to start adding in more variables or more factors, I'm going to have to move where I am relative to some of these points. And we're not going to touch reliability and safety. So there's only one that we can move on. We're going to hit that here in just a minute here. It's obviously the cost. So what are these new factors that are causing us to move off of that optimum point a little bit? One of them is incentive programs. We're all aware of this, that there are a lot of policy-based, I'll use the term distortions. That's a little too harsh, but policy-based distortions of the market. And of course, we don't have a free market for energy anyway, right? We're already a very heavily policy-distorted industry. But there has been a lot of recent effort to try to produce market incentives for certain technologies and for certain behaviors to come into play. Some of those policies, and not to be excessively political, but some of those policies are written by people who don't necessarily understand how the system works very well. So it produces some challenges for us, that things will begin showing up in places where they may not make technical sense of the system, and our job as engineers is to figure out how to put all that together. So the incentives are definitely changing the way the system works and producing some new challenges for us. They're well-intentioned in general, I think, but they produce some issues for us as engineers. Another one is system resilience. We have historically used the term security, but resilience has come into vogue recently. because we're talking about the ability of the system to continue to be reliable and safe while some kind of major, either natural or man-made event is going on. The one that you see on screen at present is Hurricane Sandy. Most of you probably recognize that. But when something like this happens and takes out parts of our infrastructure, we want a system that is able to reconfigure itself or in some way recover from this event in the fastest possible way to keep the most people online for the longest amount of time possible. And again, with some of the recent events and some of our extreme dependence on electric power in our society, this consideration has really come to the forefront in recent years and is only going to increase. And last but not least, we have sustainability. I like to show this picture because I think it's an especially cool picture. This is Wrangell St. Elias National Park. It's in Alaska. If you have never been there, I really highly recommend it. It's the largest national park in our system. It's about a little over 3 times the size of Yellowstone. It's about the size of Switzerland, but it only has 2 roads. So this is very wild space out there. The story that I like to tell is I was flying into the backcountry. I was doing reconnaissance to build a photovoltaic power plant in the park. I was flying into the backcountry with the park superintendent, and there was another gentleman with us. And this gentleman asked the park superintendent the question that everybody asks for something like this: is the park bigger than the state of Rhode Island? Everything gets compared to the state of Rhode Island. The superintendent cocked his hat back on his head and he said, "We have a glacier in this park bigger than the state of Rhode Island." It is a very, very large place. And the reason I bring this up is because we have places like this still, and we want places like this to remain available for the future. We want to make sure that we can continue to pursue our human, economic, and other activities without degrading the natural resource base to the point at which things like this simply aren't what they once were. So sustainability has become a factor that has really begun to influence decisions in energy sources and energy usage. And part of the thing that's tough for us as engineers, it's tough to quantify this. But that's a separate subject that we probably won't have much time to talk about today. So these are the new things that we have the 3 original considerations: safety, reliability, and cost. So maximum safety, maximum reliability, minimum cost. But we also want to improve our sustainability and, work with this market with these incentive programs in it, and also start working toward a more resilient system while not excessively impacting the point that we were optimized to before. As I mentioned before, I don't think anybody is going to want to compromise on safety and reliability. Matter of fact, resiliency is all about not compromising on reliability. So you can see the only thing that's going to be able to be compromised on is cost. We're just going to have to be aware of that up front. We're probably going to have some cost impacts. The key technologies that we're going to talk about here today: distributed energy resources, DER, and I apologize, I do have some undefined acronyms in here. I'll try to remember to define them as we go. The key distributed energy resource technologies that we're going to talk about here today are cogeneration. I like to put this one in first because cogeneration is a great technology where applicable, where it actually works and can be logistically managed within the needs of what the customer needs. The reason is because of the efficiency. If you have a thermal customer co-located with your plant, the overall plant efficiencies can go significantly over 80%. So cogeneration is a very, very good way to go when possible. The problem with cogeneration is that siting some of the equipment on customer facilities can be extremely difficult. So cogeneration logistically is often difficult to manage. One interesting aside that I'll toss out here: with the cogen projects that I've been involved with, it's very common that the thermal output is more valuable to the customer than the electrical output. Just tends to work out that way. Part of it is because electricity is so inexpensive. But anyway, cogeneration is an excellent technology where possible. Photovoltaics is a hot topic right now. We've discussed this. We're going to discuss this quite a bit as we go through the presentation today. There are a number of states that have solar set-aside programs that may have a renewable portfolio standard, or RPS, and part of that RPS says there's a certain percentage of the distributed energy resource that must be photovoltaic. So there's a lot of this going in right now. This is one of the areas in which I personally have the most experience, so I'm going to talk about that one quite a bit today. Let me, at this point, just mention that if there are subjects that I don't hit that you guys are interested in, please do mention them. We'll try to steer this in the direction that you want it to go. And a lot of the time, how I learn what's important and what isn't is by talking to guys like you, because you touch this every day. So I would welcome any thoughts from any of you as to what's important. Small wind is also on the list, as you can see here. By small, what I'm talking about is each individual unit is maybe on the order of about a megawatt or less, and they're typically deployed in units or pairs, maybe as many as 3, but the large wind farms, we've got dozens and dozens of these things, tend to be connected at the transmission level, so usually 69 kV or above. Most of them have dedicated protection. They may have lots of communications infrastructure to the site just because they're as big as they are. So a lot of the issues that I'm going to talk about with distribution-connected wind don't really show up in those big wind plants like that. So we're going to focus on smaller ones here today, again, because of the issues associated with them. I don't believe there's a lot of small hydro in this part of the world. If there is, somebody please correct me. We do a lot of work in the Northeast. We see it all over the place up there. It shows up all over the place in the Pacific Northwest. It is a wonderful resource where available, but like I said, it's not quite as applicable in our region, so we won't talk about that one as much today. And of course, energy storage. We would be remiss to not talk about energy storage, because if energy storage ever does become economic and robust to the point at which it starts showing up ubiquitously in the power system, it's a game changer for us. We cease to be a power provider and we become an energy provider. It decouples the real-time nature of our system, so it completely changes the way we do everything. We all know that energy storage is not there yet, and it remains to be seen how much of there it's actually going to get to. But because it is so important, we're going to talk about it some today. We, again, from the low inertia systems perspective, you might imagine we see energy storage quite a bit, especially for off-grid systems. So I'll talk a little bit about that and some of the lessons learned from systems of that type. Well, I mentioned before, I'm a little bit of a PV wonk, so we're going to talk about that in some more detail here. I wanted to start with a little bit of a historical perspective. If I move the cursor, can you folks on the phone see the cursor moving? Somebody give me a high sign if you can see it. Okay, good. There are a couple of figures that I'm going to want to point to just because things might not be totally clear. On this particular figure here, you can see this is a surface plot. On the vertical axis here, we have the cost. This really should be in dollars per kilowatt hour, cents per kilowatt hour, but it just says dollars on the axis here. Then on the XY plane down here, we have the distance from existing utility service. So in other words, this would be the length of a line extension required to serve the load. And the size of the load is on this axis here. You notice the range of loads that we're talking about here is very small. The top end of the size of load axis is only 5 kilowatts. So what this is showing us is the cost of providing electric service to a load as a function of the size of the load and the distance from the utility. So the utility is this surface here that slopes up approximately linearly, and of course it slopes up because as the distance from the existing utility service gets away, I've got a line extension. There's also a slope in the load size direction. As the load gets bigger, we need larger conductors, larger transformers, etc. The slope in that direction is pretty minimal because of the fact that that axis is so short on this graph, so you don't really see it. So this is the utility cost. And you can see that if I'm close to the utility, for all load sizes, the utility is the cheapest option. So that in general is what you would do. There's a surface here that you can see kind of curls up as I get close to the lower load size here. That is, it's labeled diesel, but that shape of surface would also apply to pretty much any engine generator set. The economics of engine gen sets are such that they tend to get a little more expensive as the size of the system gets smaller. Part of that is just because of the volume to surface area ratio thing in terms of thermal efficiency. Part of it is because there's some overhead that doesn't really scale with system size. So you see that one kind of curls up a little bit as we get to lower load sizes. And then down below, you can see this is the PV surface. Right here, along this axis where the loads are very small and the distance from the utility is relatively large, PV actually is the low-cost option. And the reason I point this out is because there is what I would call a base market for photovoltaics where PV is the economic choice. I'll show you one example later on in the presentation, but you have all seen these, the little instrument packages that you see along highways, those sorts of things that are small loads. It would be problematic for one reason or another to run a line extension. So things like that are very economically served by PV. We're doing that today. As the costs of PV drop, what happens is that the definition of far from the grid and the definition of small load begin to change. So we can serve larger and larger loads closer and closer to the existing utility cost effectively with solar as solar costs come down. Again, if you're near the utility is still almost always the lowest cost option. And you will see that if the load size goes up, the diesel curve here drops below the PV curve. So your engine genset becomes more economical as the size of the load goes up. All of these are points to which we're going to return in just a moment. I like to show this historical photo to give us a little bit of perspective of where we've been and where we're going. Photovoltaics, the silicon solar cell was discovered accidentally at Bell Laboratories in I believe it was 1954. The story, as I understand it, is there were two engineers who were both testing a silicon rectifier diode, and they were getting completely different answers and couldn't figure out why in the world their test results were so different until they realized that they were using the same apparatus, but one of them was putting a blast shield down and the other one wasn't, and the blast shield was opaque. They realized the light hitting the device was what was making the difference, and it turned out it was generating power. So it wasn't long thereafter that they thought, hey, this is of interest, and pretty soon we had the first silicon solar cells like the ones that you see in the photo in front of you right now. The efficiencies of these early devices were in the about 4% range, and the cost would have been in probably $1,000 a watt for these things. They were very, very expensive. And I love the battery connection that you see over there to your left. Apparently, NEC safety standards did not apply to batteries at this point in time, so I'm hoping they keep the young man behind the solar module there. But part of the reason I like this figure is because you see the interest. People looked at this and thought, from a slab of sand, I can shine light on it and get electricity. That's pretty cool. So there was a lot of interest in this early on. It just seemed so space age. And as a matter of fact, one of the first things we did was put them on satellites, because there we can afford $1,000 a watt. Well, obviously there wasn't a lot of terrestrial application at first, but this base market that I was talking about, where if you're off the grid, for example, if we need a little bit of electricity on a buoy in the middle of the ocean or something like that, it's tough to do that with anything other than solar. So that base market has always been there. And PV grew from there. We learned how to make better devices, how to make them more robust, how to make them more robust, how to make better systems, storage improved, so on and so forth. And as we have progressed over the years, the trend has begun to look like this. This is actually the PV module price trend. I'll show you an installed system price trend in a minute. But you can see what's happening, that module prices have been dropping and have been dropping precipitously. I was at Georgia Tech in the middle 90s, and I remember being told at the time that our goal is to get to $1 a watt device cost. And a lot of us thought, we'll get there someday, but they really didn't think I'd see it in my lifetime. Well, as you can see here, we're actually below $1 a watt at the module level. That's when I take the devices and actually encapsulate them into a package I can put into the environment. That is already below $1 a watt and still coming down. The main reason for this is industrial economies of scale. We've commoditized PV modules. So you'll notice there's a blip in the prices that appears there kind of in the late 2000s. I've been asked at several of these presentations exactly what that blip is. And to be perfectly honest, I don't know all the reasons, but my understanding is what happened there is there was a bottleneck in the supply of silicon feedstock, that the PV module industry had grown very, very quickly, and the integrated circuit industry, of course, still wanted silicon. And what happened was the silicon suppliers couldn't keep up with the demand. So there's a simple supply-demand issue that caused silicon prices to spike up momentarily. The market corrected itself, as the market tends to do, and module prices have continued to fall since. And installed system prices have followed. Unfortunately, this one cuts off in 2011. You'll notice that the prices are in dollars per watt. we are much more accustomed to using cents per kilowatt hour, which is an energy price versus a power price in dollars per watt. The reason that it's done this way is to try to compare across technologies. We need to have a figure of merit that doesn't depend on where the system is. And in terms of cents per kilowatt hour, the number of kilowatt hours I'm going to get out of my photovoltaic apparatus depends on where I put it. Right? It depends on the solar resource. So to avoid that factor in the comparison, they just do it in terms of dollars per watt. And the point of this graph is that you can see that those prices are continuing to fall. You notice that there are several different price points there for different sizes of systems. We're going to return to that one here in just a minute. I do apologize for some of the print. I see a lot of us squinting, and I have the same problem with my pop model bottom glasses here.
What is the solid blue line?
Oh, the solid blue line across the bottom?
Yeah.
The question was, what's the solid blue line there? It says Global Module Price Index. That is supposed to be a representation of the module price relative to the installed system price. You'll notice it isn't the same as the graph that I showed just a minute ago. I don't know what the index is. I don't know how they process that number. But that's supposed to show you roughly where the module price is relative to the installed system price. You can see what the rest of the balance of system is costing. You'll notice that a lot of the cost is still in inverters, but balance of system like cabling, protection, that sort of thing. Also in permitting, there are a lot of costs involved in just getting one of these systems online in terms of getting all your I's dotted and T's crossed correctly. So all of that factors in the difference between the heavy blue line and the two blue lines above. Thanks for the question. So what the price trends have driven is a deployment history that's looking like this. This is our historical data. This is where we've been. And as you can see, we're roughly on an exponential curve in terms of total installed capacity. Those of us, I think most of us have at least some engineering background. You can tell that an exponential growth for total installed capacity is slightly cheating because this is an integration, right? So the actual rate of installations is not exponential, but it's still increasing somewhat rapidly. And as a result of this, this is where we believe photovoltaic deployments are going to head worldwide up until about the year 2030. They're expecting, if the trend continues, will be at about 8% of total global generation by 2030, which is still relatively small relative to other sources. So must bear that in mind. But 8% is a huge number compared to where we are now, and it gives some indication of how many of these things are showing up on our systems today. The PV deployment trends kind of look like this, that the fastest single sector that's in terms of the number of megawatts being deployed is in these large ground mount utility scale systems. To give you just a little bit of perspective, when I was at Georgia Tech in 1996, we built the Summer Olympics were in Atlanta in 96. I felt very sorry for the marathon runners, middle of the summer in Atlanta. But the swimming events for the Olympics were in downtown Atlanta on the Georgia Tech campus. And we built, on the roof of the swimming venue, we built a roof-mounted photovoltaic array, which at the time was the world's largest roof-mounted photovoltaic system. And my recollection, the DC rating was 396 kilowatts. We were beaten, I think, in the same year by a system in Germany that was about a megawatt. But back then, a really, really big PV system was 500 kilowatts. I recently saw plans from a colleague for a system that was 50 megawatts in the southwestern U.S., and I am aware of plans for systems over 250 megawatts of solar. So these mega systems are driving a lot of the total upward trend in terms of installed megawatt capacity. Now, of course, as we talked about with the wind plants, most of those are actually transmission connected. You wouldn't put a 250 megawatt plant on a distribution feeder. So those are not really our focus today, but what we call residential and commercial scale systems. Residential scale, typically those are 20 kilowatts and less. Most of them are single phase, pretty small systems that a homeowner might put on a roof. Maybe a small business might put one of these up. Commercial systems can go up to 1 to 2 megawatts. I've seen them as big as 5, depending on the on the stiffness of the distribution feeder they're being tied to. But we're talking about low single-digit megawatts at the most. These are usually like, they may be roof-mounted systems on a Target store or Walmart or something like that. A lot of them are ground mount. They'll put them right outside the substation or maybe on a brownfield someplace. We see quite a bit of that sort of activity. But for our purposes today, the point is that they are typically distribution connected, so in your 15 kV class. The number of systems that we are talking about here is larger for this class than it is for the big ground mount systems. And the reason is obvious, right? We've got a lot of capacity, but it's spread out in a lot of smaller pieces. So there's still a lot of aggregate generation being put out there in these small systems. And because of that, we're likely to see a whole lot more PV systems being deployed on distribution feeders across the country. So that's the reason why, one of the reasons why, we are interested in today's topic. PV is only one form of distributed energy resource, but it's one that's really coming at us in a big hurry. So for those of us who are system engineers, we really want to get a handle on what are the potential impacts of this system, both positive and negative. What are the benefits we can get? We want to know that too. But what impacts do we need to mitigate before they become a problem? And that's what we're going to talk about today. Before we do, I wanted to make one comment on the subject of grid parity. We hear this quite a bit, that one of the goals of the photovoltaic community has been to reach grid parity. But the problem is, how do you define grid parity? Because what tends to happen is we will take the cost of the retail cost of electricity at a specific point of interconnection, and we will compare that with the cost of a grid-tied photovoltaic plant at that site. And by grid-tied PV plant, I mean one that does not have voltage or frequency regulation capability, doesn't have any storage, doesn't have any backup. So they'll take that plant, compare it to the price of grid-based electricity, and if those are equal, we say we have reached grid parity. If the PV cost is below the grid electricity cost, we may actually say, hey, it's better to go with PV. So start throwing photovoltaics out there and not worry about the grid. And the problem with this argument is, for us who work on the system, it's probably kind of obvious. The problem is that type of PV plant does not provide the same service as the grid does. Again, the grid's providing safety, reliability, minimum cost. Well, the PV plant doesn't have the reliability constraint, right? It's simply feeding power back into the system whenever it can, but it has no real capacity obligations. And the availability from a PV plant, I'm going to show you a slide on this in just a little bit, especially without storage. At the very best, you'd expect 50%, right? Daytime, nighttime. So the problem with this grid parity comparison is that if you're going to do that, you really ought to compare against a PV system that is a part of a system that can provide the same level of availability as the grid does at that same point. So I have a little bit of an issue with the definition of grid parity. Now, as we all know, photovoltaic plants are often installed for reasons other than just saving money on electricity cost. People are especially interested in things like sustainability. We will hit on that point a little bit later, but there have been a lot of studies on this. Photovoltaics is one of the most sustainable electricity generation technologies we have access to. When you look at the life cycle inputs to the process and the end of life disposal of whatever's left over, photovoltaics compares very, very well with other technologies. I think it's interesting that if you look at the technologies that are way down at the bottom in terms of environmental impact, so they're the most green, if you will, one of the ones that's way down there is photovoltaics. Another one is small hydro, especially run-of-river hydro. It's very, very good on that scale. Wind tends to be just a little bit higher because of the rare earths, and there's a lot of copper and a lot of cement, but it's still down there, way at the bottom of the list. But lumped right in there with them is nuclear. So just an interesting point to bring up. So that's what we're going to talk about today. Are there any questions before we go on? All right, then let's go ahead and continue. By the way, I believe the lunch break today is supposed to be at 12:30, so I'll toss that out as a logistical note for the group as a whole. But if I'm still talking at 12:30, somebody please throw something at me or something like that.
And we can be flexible. we can be flexible with that. So if there's a natural break earlier, just I'll let you kind of decide if it's better at noon or we'll just take a half-hour break for lunch.
Gotcha. I will try to be cognizant of the time. I am one of these guys that once I get on a roll, I'll forget to look at my watch. So I'll try to avoid that. You might have already deduced this from what you have heard thus far, but one of the most frequent phrases that I have to use when I do presentations like this is, "But I digress." I'll try to avoid digressing too much today. So we want to talk about the types of distributed energy resource that we're going to be focused on during this presentation. From our perspective, I want to approach this from the circuit perspective, or from like CUSP and protection perspectives. So from that perspective, the main classifications of distributed energy resource that we're going to look at can be broken down into those that use rotating machines and those that are interfaced to the circuit by an inverter. That's really it. Now, obviously, there are dozens and dozens of prime movers, but from the circuit perspective, we generally tend not to care so much about what the prime mover is. There are some reasons that we do, and these will become clearer in just a little bit. You notice that I talk about a power limitation in terms of the identity of the prime mover. Using photovoltaics as an example again, with PV, there's a current versus voltage curve that the PV is going to follow, and the inverter is going to try to put me on the maximum power point of that PV array. Once I'm there, I don't have more power to deliver. So for example, if I'm looking at a transient overvoltage situation, I can only drive the voltage so high, and then I don't have any more power to be able to go any higher. So for some of those reasons, from the circuit perspective, the identity of the prime mover may be important. But most of the time, what we're really concerned about is it a rotating machine? And then I can break that down into a synchronous generator or an induction generator. We don't use the term induction generator very often, but they do show up. They are subdivided into squirrel cage machines, which usually when they're generators, they're referred to as self-excited. I'll use squirrel cage because that's the term I'm used to, and that's the motor term, but that's also a self-excited induction generator. And then there's the doubly fed induction machine, which we'll get to in just a minute. Those are used in a lot of wind turbines. Inverter-interfaced devices, then anytime I have something that is DC or variable frequency AC, if I want to get that on the grid, I'm going to put a power converter in between. That if it's DC, we're just going to invert the DC over to AC. If it's variable frequency AC, usually what we'll do is we'll rectify it first, the DC, and then invert to 60 hertz AC. So, but no matter what is on the DC side over there, generally speaking, from the circuit perspective, all I care about is that I'm looking at an inverter, because that is what is going to dominate the behavior of that distributed energy resource as seen from the circuit. So that's the distinction that we're going to draw here today. Since Dr. Mohan is here, I had to put in at least one equation. I had to keep it simple enough that I could remember what in the world it was. But the point that I want to make from putting this up here is rotating machines are, their behaviors are very heavily determined by the physics of the machine. It's pretty much all about conductors moving in magnetic fields, right? That's what rotating machines are all about. And this is Lenz's law and Faraday's law. That's Faraday's law of induction that's up there. But the bottom line is that what determines how these machines work is I've got conductors moving in fields. I've got the strengths of magnetic fields. I've got inertias. Those physical parameters are going to largely determine how the machine behaves. And then the chief difference between the different types of machines is where the magnetic field comes from. This is a simplified equivalent circuit diagram for a synchronous generator, obviously just one phase. You can see that over on the left, you see the source of the magnetic field. In this case, we've got a voltage source that is just driving a current through coils, and that's where we're getting our magnetic field inside the machine. But the point that I want to make here, I don't want to belabor the internal dynamics of the machine, but I want to look at what's over on the right. That's the equivalent circuit model that we're used to for how to model a machine, a synchronous machine like this. And as you can see, the key point is that the machine looks very much like a voltage source behind an impedance. The reason for the voltage source is Lenz's law and Faraday's law. We just talked about it. It's the physics of those conductors moving in the magnetic fields. So I actually have a physical voltage source there. And then the impedances are largely physical impedances. I've got all these coils and wires in the machine. Those produce an inductive impedance. It's mostly inductive. There's resistance in there as well. But there's actually that physical impedance there in the machine. And this is how we're going to model it, voltage behind impedance. Those of you who work with this a lot know that if I want to look at different regimes of operation of the synchronous machine, what I will do is I will change the impedance depending on the situation I'm looking at. For example, if it's a fault, we'll have a subtransient impedance, a transient impedance, and a synchronous impedance. And we just switch out the impedance as we go through the fault characteristic so that the model represents each one of those correctly. That's generally how it works. This is a self-excited induction generator or a squirrel cage induction generator. Again, simplified equivalent circuit. You notice there's that resistor over at the right that's a variable resistor that depends on the slip. When I am driving this machine as a generator, the slip becomes negative. And what happens then is that resistor effectively becomes a source. Again, I don't want to belabor the point. We could have weeks worth of lectures just on the structure of induction machines, but the main point that I want to make here is that, again, we're going to represent this thing as a source behind impedances. So once again, voltage behind impedance model for the rotating machine. The types of generators the types of facilities that use this kind of machine are what we call a type 1 wind turbine. I don't know how many of you are familiar that there are 4 types of wind turbines. We tend to categorize them that way anyway. The type 1 is like this. It's a direct connected squirrel cage induction machine. There's no power electronics involved. Those are the simplest. They're extremely robust, but they're also fixed speed operation because they're tied to the 60 hertz source directly. So their efficiency of usage of the wind resource isn't as good as some other types. A type 3 wind turbine uses a doubly fed induction generator. I'm going to show you that in just a minute. And a type 4 wind turbine has an inverter sitting between the rotating machine and the grid. So a type 4 wind turbine actually is an inverter interface source. I don't care what the rotating machine is, but not really anyway, because that's an inverter source. So this one really applies primarily to type 1 wind turbines. Also, a lot of the small hydro plants that I mentioned that we have seen in other parts of the country, there are a lot of induction machines on some of those plants. Some of them are fairly up there in years, too. We were dealing with one not too long ago where the generator was made by International Harvester, which I thought was pretty cool. But it still works. It's pretty much all original equipment. They made stuff to last back then. This is a doubly fed induction generator. So this would be the type 3 wind turbine that I mentioned just a minute ago. What this is the rotor of the machine is interfaced to the grid through an AC to DC to AC converter. So in other words, we're going to take the variable frequency AC from the rotor, rectify that to DC, and then re-invert at 60 hertz and dump that into the grid. But the stator of the machine is directly interfaced, directly tied to the grid. So you might think of this as a partial variable speed wind turbine. It's got much more variable speed operation than a type 1 does, but not as much as a type 4. These are interesting because they combine the characteristics of an inverter and a rotating machine, and which characteristics dominate depends on the circumstances of the situation that you're looking at. We're not going to talk about this one a lot today, but again, this is one of those things that you could have an entire course on a doubly fed induction generator too. I wouldn't be qualified to give that course. The rotating machine characteristics, the point that I'm trying to emphasize here is that the behaviors of these machines are very physics dominated. So that has some ramifications that are kind of nice for us. One of the things is it means that they can be modeled with pretty good accuracy using those simple voltage behind impedance models. And with a relatively small number of parameters, we need to know some impedances, some inertias, some of those kinds of things. But once I know those things, we can plug them in and have a pretty good idea how the dynamics of this machine are going to work. So that's pretty nice. I mentioned before, and I've been harping on this, they act like a voltage behind an impedance. You'll see in a minute why I keep pounding on that point. The reason is because inverters don't, but we'll get to it. With rotating machines, and this is especially true with synchronous machines, the real power output of the machine is closely linked to the frequency, to the speed of the rotor. The reactive power then is controlled by the automatic voltage regulator, which controls the field, and that's how we generally tend to regulate voltage when one of these things is in standalone mode, or the VARs when it's in PQ mode tied to the grid. But the key that I wanted to point out here in particular is that if I have a synchronous generator operating with a load, and I suddenly increase the load, the first thing that's going to happen is the frequency of that machine is going to drop, because initially, before the governor responds and opens the throttles, the energy that goes to the load is going to come out of the rotating mass of the rotor. And as you know, that's what happens to the grid, right? If I have a big uptake in load or a loss of generation, our frequency drops. That's the reason. It comes out of the rotating mass of all of our generators. So bear that in mind. We all know this, right? This is the part we already know, that frequency really goes with real power in a synchronous machine. In terms of operational power factor, synchronous machines are usually rated down to about 0.8 sourcing VARs. You'll notice I try to use sourcing or sinking VARs as opposed to leading or lagging. And the reason is because when we're talking about a generator, leading and lagging gets really confusing. A lagging power factor in a generator means we're sourcing VARs. Of course, for load, it's the other way around. So just to be clear, I'll try to stick with sinking and sourcing. So synchronous machines can source VARs down to a power factor of about 0.8. They can sink VARs, but generally you don't want to reduce the power factor below about 0.95. They don't like to sink VARs, and they don't like to do it for a long period of time. So they're a little bit limited in power factor operation. Induction machines, especially the self-excited ones, have a horrific power factor because they're sourcing real power, but they're always absorbing VARs. They absorb VARs from the grid in order to create and maintain their internal magnetic fields. That's where their magnetic field comes from, is from us, from the grid. So they have inherently very low power factors. Usually a type 1 wind turbine or a self-excited induction generator will have power factor correction capacitors that will be co-located with the generator to try to supply some of those VARs at the site. And that's the reason why it's called a self-excited induction generator, because we've got this local excitation source in VARs. I noted on the slide, normally we're going to compensate these to about 0.9 or so in power factor, maybe more like 0.95, but they won't be compensated all the way to unity power factor. And the reason is if I did that, I would have a circuit resonance at 60 hertz. It would make the circuit harder to control. So usually these things are left absorbing at least some small amount of VARs from the grid, and the capacitors then just offset part of it. And last but not least for these machines, the dynamics are, when a transient occurs, it happens on the order of cycles to seconds is what your settling time is going to look like. So they're relatively slow in terms of how the dynamics respond. So those are the rotating machines, and that's what we might think of as conventional distributed energy resources. Now I want to talk about inverter interface a little bit, and part of the reason is as we're talking about photovoltaics and some of the impacts, what you're going to see is that a lot of the way we typically think about these things gets changed when we start looking at power electronics interface sources. Many of you have probably already noticed this is a European figure. It says 50 hertz over there on the side. But I'll show you in just a minute why I chose this specific figure. Now, as I mentioned before, an inverter is going to be used anytime I have a DC source or a variable frequency AC source. So photovoltaics, any kind of variable frequency rotating machine, like I mentioned before, the Type 4 wind turbine, flywheels will probably do something like this, batteries, fuel cells that are DC. So all of those would fall into the inverter interface category. So what is this inverter doing? What's the game here? You'll notice if you look at the schematic that's in front of you on the slide right now, effectively all the inverter is it's a big box of switches. And I like to tell this story about how many of us when we were kids didn't go to the light switch and do this a bunch of times, and our mother said, no, don't do that. Well, that's exactly what the inverter is doing. It's taking this DC voltage over here on the DC bus, you see labeled on the figure there, and then the switches chop it up in a way that there's a 60 hertz component to the chopped up waveform. Then we filter out everything but the 60 hertz component, and that's what goes out to the grid. So, conceptually, it's actually pretty simple. You'll notice that the switches in this particular example are IGBTs. That is what you'll see in most of the inverters that we're going to be dealing with. Also, notice that every IGBT has an anti-parallel diode There's a diode facing the opposite direction from the IGBT. Remember that because it becomes very important later. We're going to come back to that. You'll notice there's a rectifier shown on the left side of this figure. If the source is already DC, you wouldn't have that. It's unnecessary. If the source is a variable frequency AC source, that's where this rectifier comes in. Now, why did I pick a figure that says 50 hertz on it? Why couldn't I have done something different? Well, the reason I chose this one is because I wanted to show you that controller down there. You notice there's a lot of emphasis in this figure on the fact that there's this box, this brain box down here that says control system. And you will notice that the inputs to that controller are currents. They are not voltages. So you see that the three reference currents that are listed there, R, S, and T, again, European. But the currents coming, the commands coming into this controller, what we're telling the inverter to do, are currents. They're not voltages. All these things are going to become very important later, but the reason why that's so important is that inverter behavior is much more software dominated than it is physics dominated. Obviously, inverters don't defy physics, but the joke that I tell when we're talking about what inverters are able to do is you bring an engineer into the room with the board is sitting there, and they ask the engineer, well, what's 2 + 2? And the engineer thinks about it and says, 4. They bring the mathematician into the room, and the board says, what's 2 + 2? And she says, well, if I integrate over the Euclidean Cartesian plane and think about the intersection, yeah, I think it's going to be right about 4. Then they bring in the economist. They say, what's 2 + 2? And the economist pulls the shades down and says, what do you want it to be? That's what inverters are like, right? I mean, what do you want them to do? There's a tremendous amount of flexibility here. That you want it to operate at a power factor of 0, you can do that. Just sourcing purely VARs. That's a static VAR compensator, right? Like a DVAR is the brand name. But that's perfectly feasible. You want bidirectional power flow? You want as much going in as out? You can do that. We do that with batteries all the time. So, and there's no rotating inertia, and we don't have conductors rotating in magnetic fields. So the fact that we're going to chop this waveform up, we're telling the switches how to chop the waveform up. And we can tell it pretty much anything we want. Gives us the ability to do all kinds of things that synchronous machines can't do. Now, that's good in the sense that it gives us a lot of flexibility, but it's bad in the sense that, okay, well, how am I going to model this now? I need to model the software to get this thing modeled right. There are some generic properties of inverters that can be modeled generically. I think I just won the award for redundancy award. But the problem with this is that they are going to be somewhat manufacturer specific because they are so software determined. So generic models of necessity are going to be more approximate than we might normally like them to be. Now I mentioned before that you saw all those commands coming in were currents, they were not voltages. That's critically important because if I want to connect a synchronous generator to the grid, generally we will put it in a PQ control mode, but on the backside, it's still doing voltage and frequency control, and I'm manipulating the voltage and frequency through interconnecting impedances so that the generator looks like a PQ source to the grid. If I want it to source more power, there's a power angle inside the synchronous machine. I have to increase that power angle. How do I do that? I speed it up for just a little bit and then come back to regular speed. So it's about frequency. I got to raise the frequency slightly and then bring it back down. So it's still connected to voltage and frequency on the back side. For inverters, that's not the way it works. That typically what happens, and let me use photovoltaics again as an example. I mentioned before that I've got the IV curve. I keep drawing curves in the air with my fingers here, but with that IV curve, I'm going to try to operate on the maximum power point. How do I know where that is? Well, I've got the DC voltage coming in. The inverter's chopping it up. The inverter has these current commands, and it's sending current out to the grid, and it's monitoring the power. And it says, all right, adjust that current just by standard closed-loop controls until the output power matches the maximum of the PV array. And there's a maximum power point tracking algorithm that does this that we won't get into today. But what you can see is that the inverter is not doing anything with voltage and frequency. It is relying on the grid, on us, to provide voltage and frequency. And then it's sourcing a current into that voltage and frequency to produce the desired power. So the inverter is going to act like a power-controlled current source, not like a voltage behind impedance. There are some really critical ramifications for this that we're going to get to in just a minute. One of them is that the fault current from this inverter is going to be relatively low. As you guys all know already, if I fault a synchronous machine, I can get fault currents that are on the order of like 10 per unit. Usually we try to limit it to something more like 5 using grounding impedances and things like that so that we don't damage the generator. But synchronous machines, again, because it's a voltage behind impedance, and that fault impedance looks like a really low impedance load from the generator's perspective, that voltage is going to shove a ton of current out there. Inverters don't do that for several reasons. One is, as I just mentioned, they're current-controlled devices, and they're trying to maintain constant power. So they're not going to shoot up to many times per unit. But the other thing, which is somewhat buried in this, is I mentioned these are semiconductor switches. The devices that are doing the chopping up of the DC inside the inverter are semiconductor switches. Semiconductor switches do not like overcurrent at all. Do not ask me how I know this. But these devices are going to be heavily protected because, again, the standing joke is that your $50 IGBT will always fail to protect your 50-cent fuse. That's what we're trying to avoid. So the controls, a lot of the protection in these things are specifically geared to make sure those currents don't get too high. Usually baked right into the gate drives on these IGBTs, there will be both peak current controls and RMS. RMS is a little slower, obviously, but it's also monitoring that peak current. And if that spikes above a certain value that the IGBT manager doesn't like, it's going to say, whoa, something's wrong. It's going to block the gate signals. So these things are extensively protected against the currents going too high. And what that means is our fault currents for a three-phase, typical utility-connected three-phase inverter, we're looking at about 1.2 per unit for the fault current. And actually, in a lot of cases, it's lower than that. And I mentioned before, there's going to be a limited ability to drive over voltages because in cases we might expect the over voltage to go up to a certain level, but that would require a certain amount of power. So as the voltage begins to rise, I simply do not have the power to push the voltage any higher. One important characteristic here is that when you look at the frequency of an inverter, the inverter's frequency is much more closely related to VARs and to the phase of the output than it is to watts. And this is part of the reason why I was emphasizing that for the synchronous machine before. It's backwards in an inverter. Why? Well, because as we mentioned before, the power is actually controlled by changing the magnitude of the output current directly. So we don't have to speed up frequency or anything to change power. There's no coupling there. But how does the inverter know how to synchronize to the grid? How does it know what the waveform should look like? Usually there's a phase lock loop or something equivalent to a phase lock loop in the inverter. And it is watching the terminal voltage. Then it's going to start moving its sine wave reference by changing the frequency to line up with that utility voltage reference. And then it'll start sourcing current on out with that waveform reference. But the way the phase lock loop works is that it sees a phase error and then it accelerates or decelerates its frequency to pull into phase. Now, that, of course, that's the phase of the output current that we're talking about. So frequency and VARs tend to be directly related in an inverter. So it's kind of counterintuitive for us. I mentioned before, what do you want the power factor to be? It can be anything you want, right? All the way down to 0. There are capability curves. The inverter has a certain, you have P and Q. If you do your PQ triangle, there's an S limit, right? The apparent power S limit. So you have to stay within that, just like you do in the sync gen. But as long as we do that, then we can operate at any PQ combination within those limits. And then the last thing is the dynamics of inverters. I mentioned before that sync gens, we're looking at cycles, maybe seconds for transient to damp out. Inverters are much faster than that. There's no rotating inertia, right? So they don't have to wait for those kinds of things to stabilize out. Inverters can respond in single-digit cycles pretty easily, and in some cases, for certain phenomena, it can be well into the sub-cycle regime. In some cases, just a few microseconds. So they're, relatively speaking, they're very, very fast. Part of the reason that I bring all this up is that it is not at all an uncommon thing that in modeling software or in various analysis scenarios, you might be in a position where you are asked to model a distributed energy resource that is inverter interfaced, but you don't have the inverter model readily available. And a lot of times people will say, just new model is a generator, just throw it in there. Well, if you're doing purely a steady state simulation where all you care about is PQ and P and Q aren't changing, you could probably get away with it in that case. So, like if I'm just looking for voltage rise or thermal loading or things like that, that may work. But as soon as there's any dynamics at all, you can't do this. The inequality that you see on the screen in front of you kicks in. Inverters, if there's going to be a fault, if there's any kind of a transient case, any of those things, you cannot model an inverter as simply one type of generator because they are that different. You're going to get the wrong answer. So bear that in mind. Toward the end here, I'm going to try to be cognizant of the time so that by the time we get to the end of this presentation, I'm going to talk a little bit about how you make sure that you have the right model for the right purpose. One thing that I wanted to make sure that I said here is that I don't want to overemphasize the difficulty of modeling inverters either, because in a lot of cases, a lot of software packages will model the inverter as either as a constant current source, for example. And again, if it's a steady state situation, which is the majority of what we deal with, right? When you're dealing with conductor type sizing and things like that, you can get away with that kind of thing in a lot of calculations. So it's not all bad. It's just there's some specific cases, some of which I will show you today, where you're going to get completely the wrong answer if you go that route. Okay, so that's an introduction to the technology specifically that we're going to look at today. So the next module, module 2 here, is all about the impacts that these distributed energy resources have on distribution circuits. I'm going to focus mostly on inverters, but there's going to be a lot of sync gen stuff in here as well because we see a pretty good number of them. So we're going to start with some of the voltage impacts. And I will ask your forgiveness before I start this because you got an outline where it sort of broke down how the presentation was going to work by time. The contents on that outline are pretty much what we're following here, but I totally messed up the time distribution. Module 2 is by far the longest one here. So we'll try to keep things distributed in terms of lunch and things like that and natural breakpoints.
We'll probably want to take a break around 10:30.
Okay, so we'll make sure we do that. Okay, so we're going to start with some of these voltage impacts at this point. Sarah's comment there for those of you on the phone is we're going to try to take a break right around 10:30. First one I want to look at is voltage rise. We'll start with sort of a generic feeder circuit representation here, and I am still lamenting this. I don't know why I didn't put a tap changer or a line regulator on the circuit, but I've got capacitors, loads. There's a couple of distributed energy plants on here, which I have represented as PV. You see the utility at the left with a source impedance. There's a substation transformer, which in this case is delta to grounded Y. I didn't show the ground. I should have. And then the rest of the feeder from there with the feeder impedances and so on and so forth. Now, as you all know, if I didn't have any kind of distributed energy resource on the feeder and if I didn't have capacitors, there's going to be a voltage drop along this line as the current from the utility flows through all of those feeder impedances. There's going to be a voltage drop on each one of them. So by the time I get out to loads 5 and 6, the voltage is going to be lower. So typically we mitigate that by, we can put in capacitors to give us VAR support, prop up the voltage at various points on the feeder. You can put in a line regulator, which is a tap changing auto transformer that will, again, step the voltage up at certain points on the feeder, trying to mitigate this problem. If I put distributed energy resources out there that are now pushing current back toward the grid, then what happens is the voltage drop that the loads were seeing becomes negative because the current's flowing the other way, and that's a voltage rise. That's all it is. It's a negative voltage drop. This can occur on sections of feeders, and it's going to happen anywhere, on any subsection of the system that is exporting power to the rest of the circuit. The level of voltage rise that you're going to see is very strongly dependent on a number of factors. One of the biggest ones, of course, is the power factor at which the distributed generator is operating, distributed energy resource. Most of the time, and this is especially true for photovoltaics, but it's also true for most of the sync gens we work with, they operate them at unity power factor. So there is no VAR input or output. You can schedule these things to operate at a fixed power factor. Many inverters have the ability to work on a time-scheduled power factor. And we're going to talk about this quite a bit more in a little bit, but newer inverters are now being required to be able to operate with volt-VAR droops. So they have a dynamically variable power factor. California is driving this, as California tends to do. Their Rule 21 is their distributed resource interconnection requirements document. And California Rule 21 is requiring a bunch of new, what people tend to call smart inverter functions. I think of them as grid support functions. But these capabilities must be built into inverters. So most of the inverters that we're going to see going forward are going to have those capabilities built in. We'll talk a little bit later about how you could use them to advantage. You notice that I mentioned here that you can actually set a distributed generator to absorb VARs. Well, if I did that, I could pull the voltage rise down, right? Because the real power is trying to push the voltage up, but the VARs, since they're flowing the other way, are trying to pull the voltage down. So there's some benefit to actually having the distributed generator sink. Did I say source? Having the distributed generator sink some VARs, absorb some VARs. We're going to talk about that a lot more in just a minute when we start talking about impacts on regulators, but bear that in mind. We're going to look into that here in a minute. Obviously, the voltage rise is also very dependent on location. Where are you on the circuit? Because it's critically dependent on the circuit impedances. Here are a couple of examples. This is a case in which there is a distributed generator out on the feeder, and you'll notice that the locations are given generically. You'll see a number of things in this presentation like this, that because feeder locations and geographic information are all CEII, all of those have been stripped out of this presentation. But you can see here that basically we just listed 5 generic locations. Location 1 is the substation, and there's a capacitor at location 2. There's a capacitor at location 4, and the PV plant is also at location 4, so it's not quite at the end of the feeder. You notice there are 3 cases here. The middle case, the dashed case, is kind of our baseline. There's no PV in there at all. You'll see that the substation end is running a little hot, which is what we tend to do. And then the voltage drops away from there as we go out to the loads, which is what we expect. If I have the PV plant out there, if the PV plant is sourcing VARs, so in other words, it's acting like a capacitor to the circuit, you'll notice that what it has done is it has really flattened the voltage profile, which is a good thing, right? That's what we want. We want nice flat voltage profiles on these circuits. So at least theoretically, the PV could act as an asset if we had it doing that for us. We might want to tone down the substation head end just a little bit, but theoretically there would be an OLTC up there that would do that, and that's not shown in this particular plot. We can also have the distributed generator sinking some VARs, absorbing VARs, and that pulls the voltage down. And you see what happens there. That in this particular case, that might not work so well because the voltage is getting a little low toward the end. But you may have noticed the heading of this figure. It says heavily loaded feeder. So this is a peak loading case. What happens when the feeder is lightly loaded? This is what happens. You'll notice, again, if I have the DG sourcing VARs, I've now pushed the substation head end above 1.05, and as I'm getting down toward the end of the feeder, we're about 1.08. It's getting a little warm, so this would not be the best way to do this. If I have the DG sinking some VARs, then again, the voltage profile stays within limits, and you'll notice that if there's no DG at all, again, for the lightly loaded case, the voltage profile flattens out, which is what you'd expect, right? There's less current being delivered to the loads. So this one would be a case where, well, operating sourcing VARs might not be such a good idea unless you can do it adaptively so that the PV plant kind of knows what's going on with the load and changes its VAR output accordingly. That's where some of these grid support functions will kick in. We'll talk about that in just a minute. Why do we care about voltage rise? Well, it's the obvious issue, because if the voltage is too high, it degrades customer equipment, and it also degrades our equipment. The lifetimes of things drop. This is especially noticeable with incandescent light bulbs. I'm going to show you a graph that demonstrates this in a minute, but it's also easily demonstrable with capacitors. Right? Dielectrics there's an Arrhenius curve where they do not like overvoltage, and their lifetime will drop as the level of overvoltage increases. The same thing happens with insulation, right? Which is, again, also just a form of dielectric. So the overall picture here is that equipment will die faster if we let the voltage ride up too high. There's an increased power draw from the utility. The conservation voltage reduction is CVR. And again, I don't know how many of you actually use CVR in your systems, but in a lot of northeastern systems, and it's done sometimes in California, if you've got a peak demand problem or for some reason a really heavy loading issue on a feeder, you can use the substation OLTC or line regulators to start pulling your baseline voltage down just a little bit, and the constant impedance load on the system then will draw less power. So the idea is you can moderate voltages a little bit. CVR is becoming less and less effective going forward because there's more and more constant power load. So that's an issue, but that's a separate issue. But if I drive the voltage up, I've got exactly the opposite problem. All my constant power load is going to draw more power. So it's the opposite of CVR. The other thing is we've actually seen some cases where the overvoltage gets high enough for long enough that the distributed energy resource actually trips itself off on its own induced overvoltage. The applicable interconnection standard for distributed energy resources in the U.S. is IEEE 1547. There's a whole bunch of parts of it. You'll hear me refer to 1547.xyz. All that's a part of the 1547 family. 1547, at least as it stands right now, has a pair of default overvoltage trips in it. And the lower one is it's 1.1 per unit for 1 second. If you're at 1.1 per unit voltage on a per phase basis, so it's each individual phase, for 1 second or more, then the DG is supposed to trip. There's another one higher than that. It's 1.2 per unit for 160 milliseconds. We've seen cases where the DER actually drives the voltage above 1.1 per unit for longer than 1 second. It pops itself off. So obviously that's a fairly extreme case because 1.1 per unit is not a place where you want to be for an extended period of time. What happens if you do let the voltage ride up? This is a light bulb case I was talking about. It turns out that the lifetime of an incandescent light bulb is inversely proportional to the fifth power of the overvoltage, the amount of delta V we've got above nominal. So if you take a look at this curve, you can see that if I get up to about 1.05, about 5% high in my voltage, we've already lost about half the lifetime of the bulb. So this is one of the more dramatic loss of lifetime impacts as these things go, which is part of the reason why I show it, because it's interesting. But as I mentioned before, all other types of insulators and similar devices, dielectrics, are going to have a damage curve, and they are going to have a similar situation where lifetime degrades as the voltage goes up. So it's important for us to keep voltages well regulated. Most of you already do this. I'm just showing it because it's interesting. How do you mitigate voltage rise? We're going to talk about some of the methods a little bit later. One of the first ones is reconductoring. If the problem is that the circuit impedance is too high, change the circuit impedance, reconductor it. I'm sure most of you are already aware of the issues associated with that, because if you've got a DER owner-operator who wants to put a plant on a feeder, generally they would have to bear the cost of the reconductoring, and that makes them really happy. So that's where you start getting letters to your PUC and things like this. So generally you don't want to recommend reconductoring if you don't have to. Line regulators can help. The problem is you can really have line regulators banging away to try to regulate the voltage on a weak feeder if you've got a variable plant at the end. So we're going to come back to that point in a minute. You can limit the amount of DER that you allow on that specific circuit. The circuit wasn't designed for it, right? We all know that it's common on distribution feeders that the conductor size gets smaller and smaller as I go out toward the end. We've talked about optimizing the system for cost. That's why we did that, right? Well, it's simply not designed to hang a 5 megawatt photovoltaic plant on the end of a long, skinny feeder like that. So what you can do is say, look, this is all the DER the circuit can handle. You can't put any more. Again, that is an option that causes a lot of frustration with project developers. So basically, we talk about closing feeders, quote unquote, and that tends to generate a lot of negative publicity. So, well, what else can we do? Well, we can have the inverters absorb some VARs. I talked about that a minute ago. We're going to get to it again in a minute. Longer term, what we want to be able to do is go to these active volt VAR controls. So that's all forthcoming. So hold those thoughts because we're coming back to it. The next subject I want to talk about is voltage modulation or flicker. And you notice that I've separated those out because a photovoltaic plant will cause some modulation of the voltage as clouds go by, because the output is going to go like this. The thing about voltage modulation and flicker is that, strictly speaking, flicker is a voltage modulation that is periodic. So it's got a known fixed period. The voltage modulation that we get from PV plants isn't really periodic, so technically it's not flicker. We still call it that, and I will probably use the term somewhat interchangeably, but the reason why it's important to differentiate them is because the standards we have, the applicable standard here is IEEE 1453, and the standard is a flicker standard, not a voltage modulation standard. So you just have to be a little careful how you apply it. There are some correction factors and things that, if you look at 1453, there's a huge appendix that comes along with it with a whole bunch of papers explaining how to use it, and you just have to go through that a little bit and make sure that you're properly using those PST and PLT values for flicker. But I want to talk about flicker first because, I mean, is flicker a problem with photovoltaics? Generally speaking, it is not. There was a time when it was, because there was a common active anti-islanding method that involved putting out a pulse in the VARs, and it was called impedance detection. And what the inverter would do is it would shift its phase momentarily, put out a VAR pulse, and see if the frequency changed. In other words, if the phase lock loop started lining things up again. If the inverter was able to change the frequency by adjusting VARs, then the inverter would say, I shouldn't be able to do that. The grid must not be there, and it would trip offline. That was in classic impedance detection. But the problem is that we have these inverters that have like a square wave pulse in the VARs, and you can imagine what that did with voltages. Most commercial inverters today either use a different method or they have some mitigating strategies like using ramps and things like that help that not be so much of a power quality issue. So generally speaking, flicker is not an issue with modern photovoltaic inverters. Here's a historical case where it was. This is a pair of voltages, the blue one at the substation and the red one at the PV point of interconnection, in which this was an inverter that was using just a straight pulse-based square VAR pulse to do anti-islanding. And as you can see in this case, the voltage modulation was unacceptable. This was a case where I can't remember what the specific PST value was, but it was over 1. So it was a violation of 1453. And I believe in this case, the mitigation strategy was actually to switch inverter manufacturers. They just went to a different inverter that was doing something else. So that's flicker. Generally, strictly speaking, flicker is not a worry. How about voltage modulation? Well, voltage modulation is directly related to voltage rise, right? Because voltage rise happens because the PV output is causing a negative voltage drop. As the cloud comes over, PV output decreases. The level of voltage rise being produced by the PV output also decreases. So you see a modulation in the voltage in the area where the PV plant is. Same kind of thing happens if I have a wind plant, when I have a drop off in the wind. There are other types of intermittent resource plants will have an equivalent effect that causes voltage modulation like this. So, and as I mentioned before, strictly speaking, it's not flicker. The reason why that's important is you have to be careful how you apply the standard. Now, we should be talking about mitigation of voltage modulation. I'm going to come back to that point because one of my topics here in a minute is impacts on tap changers, and that's where voltage modulation gets us into trouble, because voltage modulation will cause those tap changers to bang away trying to fix the voltage. That we need to mitigate. So we're going to discuss in a minute how to do that in that section. Wanted to just briefly mention harmonics. I talked before about, these inverters are nonlinear switching devices. Obviously, they do produce harmonics. Is that a problem? Is that a worry for us? In the harmonic standard that applies here is IEEE 519. And I mentioned before IEEE 1547, that's the interconnect standard. It references 519. So this is supposed to kind of all be tied together. But inverters, photovoltaic inverters are supposed to obey IEEE 519. And it turns out that almost all modern photovoltaic inverters do. I have not yet really come across one in the last 10 or 15 years that had an actual output distortion problem. Usually current harmonic distortion levels are less than 3% for all inverter power levels over maybe 50% or so. And they're all IEEE 519 compliant because they have to be 1547 compliant. We get some questions once in a while about whether having multiple inverters causes a problem. Do the harmonics add in some way? And the thing is, because the switching bridges don't tend to talk to each other, a lot of time the harmonics aren't strictly correlated. So a lot of times when you have more than one inverter, the total distortion from a plant is actually lower than it is from an individual inverter. So far that has not been much of an issue. I mentioned here that in general, with these types of inverters, harmonics really aren't that much of a problem. had to throw in one Fourier transform, right? So this is the Fourier transform of the output current of a residential inverter. So this is a relatively small one. I believe this one's 5 kilowatts. But because it's single phase, you see that the triplet harmonics are all in there. We've got third, ninth, all those. And the thing that's interesting to notice is that the total harmonic distortion is still considerably less than about 2.5%, even with the triplets in there. By the way, this inverter for this test, if I'm remembering this right, was operating at about 67% power, about 2/3 of rating. It's important to bear that in mind because inverter current output distortion does rise as the power level goes down. So if you get below maybe 20% power, maybe somewhere in that range, depending on the specific inverter, the total harmonic distortion will begin to rise, and it can start to get pretty high at really low power levels. I've seen total harmonic distortion levels get up to like 20%. Now that's still generally not a worry for us because remember 519 is a harmonic current injection standard. And because we're at such low power levels, the distortion is coming from injected currents that overall are still pretty low. So it's still not a 519 violation. Generally speaking, it's not going to be a problem for us. There's one thing that you want to watch for, and that's resonance. I mentioned here a transformerless inverter. I imagine many of you have probably heard of transformerless inverters. This is what people are hawking these days. With photovoltaic inverters, they used to have 2 transformers associated with them. One of them is what we would call the generator step-up transformer, also sometimes called the distribution transformer. But you'll have a 480 volt or some low voltage AC bus, and I got to get up to my feeder voltage. The GSU transformer is the one that does that. Then inside the inverter cabinet, there typically was a second transformer that we would call the isolation transformer. The main reason that was there was because back at that time, DC voltages were limited to about 600 volts by the protection equipment and by, I think ADC might have actually limited us at that time as well. But it had to do with safety requirements more than anything. So in a photovoltaic array, if you design for 600 volts, the voltage that you get from a PV array depends very strongly on the array temperature. And of course, when it's under sunlight, the array temperature is going to go up, the voltage is going to come down. So a 600 volt array doesn't operate at 600 volts, it may be more like 400 on a hot summer day. The inverter circuit that we use has to have the DC voltage higher than the peak of the AC voltage. If it isn't, the power, we can't drive power from DC to AC because the voltage ratio is backwards. So we had to make sure that that DC voltage was always higher than the AC peak. We were limited on the DC voltage, so what they did is they put in this isolation transformer that took the 480 or whatever it was, and then dropped it down to some much lower voltage, say 200-ish, somewhere in that range. And that's what ensured that we could continue to keep sourcing power out. Those isolation transformers, there's actually some really nice properties with them. As you know, transformers give you magnetic isolation. There's a lot of good that comes from that. But of course, they absorb some power. Transformers have some loss associated with them. So inverter manufacturers are grabbing for those last few percentage points of efficiency, have started eliminating that isolation transformer. And there are a couple of ways you can do that. Now we can go up to 1,000 volts DC. So there's a lot more headroom there. You can also use boost converters on the DC side. And we won't get into that in a lot of detail here. There are some advantages to doing that. But you can have the DC side handled by a set of boost converters over there. Bottom line is that it is possible now to get rid of the isolation transformer. The GSU transformer, of course, is still there. I don't think I've ever seen an inverter that interfaces directly to 1247. So to call them transformerless is a tiny little bit confusing because there is still a transformer there, but the transformer in the cabinet is gone. Now what happens when you do that is a lot of times we used to use the inductance of that isolation transformer as a part of the T filter on the output. Now that's gone. So the grid can now see the filter capacitor more clearly than used to be the case in the past. We've seen a few cases, especially for higher voltage interconnections. This usually is a transmission level issue, not so much distribution. But at transmission, we've got a fairly good sized inductance, but the resistive part of the impedance is really low, right? Very low loss at transmission. What that means is if I have a case where that output capacitor in the inverter clearly sees the inductance of the system, I've got a resonant frequency there, an LC tank. And the R value of transmission is low enough that it's not very well damped. So you can see cases where there will be a resonance problem there. You'll start to see overvoltages because of this resonance between the output filter elements and the rest of the system. If that happens, you can identify it with a transient study, and usually the mitigation is a trap filter. So it's not that hard to solve, but you need to be aware that it's there. Again, I don't know that I've seen this problem at distribution. It's more for higher level interconnections, higher voltage interconnections, where the resistance of the interconnection is low.